Hello, everyone. Welcome to Theo-MathProblemSolver. In this particular episode, I'm so excited to take you through the journey of first-order linear differential equations. For now, we are going to look at the homogeneous linear differential equations. As if time permits, we'll also be looking at the non-homogeneous linear equations. So let's start with the homogeneous part. Now, a simple but important and useful type of separable equation is the first order homogeneous linear equation. Now, a first order homogeneous linear differential equation is usually of the form y prime plus some function, let's say which is a function of t, y equal to 0. Okay. Okay, good. So such a linear differential equation is called what we call a homogeneous. Okay, besides such a linear differential equation is homogeneous. Okay, and as time permits, we would look at it from a different angle so that you really appreciate it. Now, we said that it can be also done in a very separable way, which means that this can also be written as this. So this is also equivalent to y prime equal to minus um, p of t and y. Okay, the y prime in this case, the y prime is the same as dy dt. Okay, if I say y prime, which is the first differential, okay, the y prime means the first differential. I hope that's okay. Very good. So when you say the y prime in this differential equation, we are referring to the first derivative. Okay, very important. Let's get going. Now, if you have be following us over the months, we've seen a first order homogeneous linear differential equations, namely the simple growth and then the decay model. Okay, so the simple growth. Let me use. So there's a simple growth or the decay model. We look at it in the previous content, and we said that y prime is equal to k y. Okay, this is a simple growth or the decay model, which if it's decay, that means that k would be less than 0, and if it's a growth, then k will be positive. Okay, we look at it, if you could recall, and by this time around, we kind of look at it from kind of it's a bit different from what we've seen. Okay, what we have encountered in previous episode, but this one is a step further. Okay, so I'll take my time to really help us to grasp the concept so that when we are being confronted with an issue or a problem, we'll be able to leverage the technique to solve such a problem. So let's get going. Now, since the first order homogeneous linear equations are separable, okay, like the case of this. So we say separable, it means we can write it this way. It's separable, okay? It's separable. Then it means that we can write them in the usual way as this, as I've underlined here, okay? So let me pick that. So from here, so I said that the first differential equation can be written this way because it is what separable, in other words, okay? Very good. Now, we want to solve such a problem. So what do we do? Now, how do we solve such a problem? So we want to, since we are saying it's separable, in other words, we want to group the dependent variable on one side and the independent on the other side, okay? Or the y's on one side and the other component on the other side, okay? So the easiest way you may want to look at it is to kind of write it this way, okay? Very good. Now, over here, what you want to do is that, so usually what I do is that, so this is also equivalent, or this can also be written as, okay, let me do a very nice thing here. So this can also be written as I mentioned, this can also be written as dy dt, okay? Because y is with respect to t, with respect to time, okay? Now, what I would do is that, you can, so this, in other words, if that's the case, it means that this can also be written as dy on y, okay, equal to f of t dt, okay? Just from here, if you want to kind of, link them, that kind of makes it a bit okay for everyone to get it. Now, what I will do is that then I will take the integral because of the dy, the change in y, okay? So I will take the integral on both sides, okay? Then I'll take the integral on both sides. Now, if you recall, we learned that the integral of 1 over x is what? Is a natural log of x, okay? Plus c. It's because it's an indefinite, okay? And it's the same here. It's the same thing here, okay? So if that's the case, then it means that the integral of dy on y is what? The natural log of y, okay? Now, what is the integral of this? Okay, what is the integral of this? Now, because p of t, okay, which is an integrand, has not been defined explicitly, and according to the fundamental theorem of calculus, the integral of small t is what? Is equal to big F, okay? But in such an instance, I wanna say big P. Suppose that this is a small p, then it becomes big P, okay? Then plus, since this is just an indefinite integral, so we add some constant, let's call it C, okay? Very important. Let's get going. Good. Now, having this, we want to find y and not length of y. So what do we do? There's a relationship that kind of exists between the natural log and then the um, uh, exponential function, right? Okay. There's this relationship that kind of exists between the natural log um, 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 and then e. Okay. How do we do that? They're all less constant. Okay. So what we can do is that we can take the e to the power the natural log of y, then whatever we do on the left, we do on the same on the right. Okay. So big P of x plus c. Okay. Now I want to point out that the Euler's constant raised and the Euler's constant, which is the exponential function, and then the natural log, they are inverses of each other. So when that happens, it means that the e and the natural log will cancel themselves. So you have y to drop. And then over here, this can also be written as e to the power big P of x, and then e to the power c. Okay, good. Now this e to the power t, so we have big e to the power big P of x, then e to the power c is still a constant, right? So let's suppose that that constant, this is just a constant, okay? E to the power c, remember c is any constant, right? So, and e is also is a or less constant, right? So e to the power a constant is always a constant. So let's suppose that that constant is big B. Do you see that? Suppose that that constant is big B, okay? Is B, some B is also a constant. So it means that the solution to this particular problem, has been, the general solution of this particular problem has been given as this. So basically that's what we have got so far, okay? And I want to point out that big P of x is an antiderivative of negative of small t. Is that okay? Very good. Let's pick an example so that we'll be able to kind of appreciate what we are doing. Okay. So as an example, suppose example one. Example one. So solve the IVP. So IVP stands for initial value problem, okay? IVP, that is initial value problem, okay? Y prime, the first order differential plus y cos t equal to 0, okay? Good, 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 good. Now we said that such a problem is separable, and we kind of look at it from a different angle, right? So we said that when you're given such a problem, usually what happens is that we can write it in this form. But you see, when we compare this to what we used to have, now let's start to solve this. Now, our given problem, which is y prime price plus y cos of t equal to 0, when we compare it to our original form, which was y prime plus p of t, y equal to 0. Remember this. So which means that my p of t in this case is what? Is cos t, right? If you compare, we saw that it's like that. But remember, we mentioned that such such a problem is separable, and we explained what separable mean, right? We kind of explained that. If you could recall, we kind of explained it in simple term. All right, now let's get going. Now we said that the big T, okay, if you look over here, when you look over here, we said that this big T, P is the antiderivative of the small t here, of a small p here, okay? But if that is going to be a problem, you may want to solve it straight away. If that's going to be a problem, we can just go straight to the point so that we don't have to find ourselves wanting, right? So in that case, we're going to have y prime equal to the minus of what? Y cos t, okay? Then because it is separable, it means that my dy, remember we also said that this can also be written as so dy dt, okay? Equal to y cos t, okay? Now, for the sake of separability, we can write this as this, okay? Good. Now, what happened is that we can take the integral on both sides, okay? So we take the integral on both sides. And we said that the integral of this, we're just going to be what? The natural log of y. We can add some absolute here equal to. Now, the question is, what function do we differentiate to get cosine? That is sine, okay? So we're going to have minus sine of t. Then we add some constant c, okay? Now, remember that we said that to find y, remember over here, we don't need the natural log of y. We need y. So what do? We can exponentiate both sides, okay? By exponentiating both sides, we are going to have a to the power times a to the power c, okay? And then we said that since the exponential function is it has inverse with has some inverse with the natural log, because we said that they are inverse of each other, that means that we're going to have y, okay? And then remember e to the power c is a constant, so we can use something like b or any other constant, okay? So this is the result we are going to have for this particular problem. So that's the result. So suppose that the question went further to say that such a problem is subjected to maybe a constraint. Suppose it was said that this problem was subject to maybe some constraint, like maybe y of 0 is equal to maybe half. Now, since that if that's the case, if there's a constraint on the problem, then it means that with this general solution, so this is what we call the general solution, okay? This is what we call the general solution. The general solution means that the problem has not been restricted within a particular time range or a particular domain, okay? Okay, so that's a general solution. The general solution holds for, it means that at every point in time you can get a solution. Okay, when the constant b has a solution, you get another solution. When the constant is 2, you have another solution. When the constant is 3, now if we decide to say no, at this time around we want the constant to be so and so, or we want at this time we want the constant to be this, then that becomes what a particular solution. So in such an instance, we want to go further to find a particular solution. But what do we do? Now, remember that with our restriction, we have, mind you, that the y is a function of t. Y is a function of t. Now, if we are given this condition or restriction, then it means that wherever I see t, I should just replace it by 0, okay? So on that note, my y of t will be equal to be to the power minus sine of 0, okay? Then I should equate the result to what? To half. Is that okay? Good. Now, what is sine of 0? Sine of 0 is what? Is 0. But e to the power 0 is what? It's 1. Any number to the power 0 except 0 is what? Is 1, right? So on that note, we're going to have b to be equal to what? Half. Is that okay? Good. So if that's the case, it means that this means that our particular solution, okay? Our particular solution is given by y of t to be equal to half e to the power minus sine t. Okay? So now it means that we have our solution. Does that make sense? I hope that makes sense, right? Good, 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 good. That is what this problem is all about. And at this point, if you have not subscribed, please do so. Like, comment, share our content with your colleagues, with your loved ones. Let's help, demystify the myth around mathematics. Thank you so much. Bye-bye.